Welcome to Future Talk. On today's program, we're going to talk about the use of nanotechnology to develop new kinds of materials with a range of practical uses. I have two guests, Professor Yi Cui and Professor Sarah Heilshorn, both of them professors of material sciences and engineering at Stanford University. They're both members of the interdisciplinary Gabal Laboratory for Advanced Materials, and they both have their own laboratories staffed by graduate students, postdocs, and visiting scientists, where they do basic research into the properties of matter at the nanoscale level and try to apply that knowledge to real-world problems. Yi Cui's research is focused on energy storage. He's developing lithium batteries which can store much more energy in a much smaller space than the current lithium batteries, which could have a huge impact on everything from mobile electronics to electric automobiles. Sarah Heilshorn is focused on developing new biomaterials made entirely of engineered proteins for use in regenerative medicine to cure bodily ailments. And I'd like to welcome both of you to the program today.
Thank you.
Yi Cui, let me start with you. How's your progress in developing these batteries? I understand you're doing very well, and we might see something on the marketplace sometime soon.
Yeah, we have been making quite a bit of progress in the past 5-6 years. As you know, batteries now for high energy applications, cell phones and laptops and transportation is dominating by lithium-ion batteries. In order to improve lithium-ion batteries further, the key is the materials inside the batteries, which can store lithium ions, can store electrons. So we invented a new technology, for example, silicon nanowire technology that can store much more lithium ions, up to 10 times more than graphite carbon used in the existing technology.
I understand we actually have some slides which can demonstrate some of this. Can we see that first slide, please? Okay, yeah. So what are we looking at here?
So the slide you are seeing is the comparison of silicon nanowire, that's in the B, the figure B, compared to the traditional of using film, big particle, that's in figure A. For silicon, it can store 10 times lithium compared to carbon, but the volume expansion is too much. Those big particles are going to be broken, the film will be broken. And by using nanowires, their diameters are small enough. There is a space around this nanowire, they can expand without breaking, so you can charge and discharge these batteries for many, many cycles.
So to make this work, you have to solve a lot of very complicated problems.
That's right.
Okay, and we have another slide. Can we see the next slide, please?
So the next slide is now change the topic a little bit. Everybody knows that the battery safety is so important. And we see the plane can catch fire, you know, due to the
batteries can explode, overheat.
That's right.
Okay.
And the cell phones, you know, the laptops, sometimes you see the news catching fires. So the main reason, you know, they can catch fires is the internal short during batteries usage. Now we have a new invention. In this figure you see right there in the bottom, we have this the middle dashed line, that's a nano layers of conducting copper sitting between the two battery electrodes with a positive sign and the negative sign.
So right they can't short out, the negative can't jump into the positive?
That's right, there's a separator right there, separate them apart. Now what happened right there is this red color dash coating. When this shorting happening, it touched the middle, and this middle layer will detect this shorting by measuring the voltage. It becomes 0. Now at this moment, the battery is still safe. It's not shorting all the way from negative to the positive, so to prevent battery catching fires.
But it doesn't fix the battery, it just warns you that it's no good.
That's right,
doing damage.
It warns you. Now the research ongoing in my lab is try to remove those shorting by doing some smart function in our materials.
Now I understand you have one more slide. This one is not related to batteries, but it is related to your nanowires, another application. Can we see that?
Yeah. What you are seeing right here is we try to accomplish a new type of water filtration technology which can kill bacteria and viruses with low cost, very fast, high efficiency. And given the problem now California have, we have the drought problem. We don't have enough water, so we need to recycle the water. This type of technology allow you to do is having nanowires which generate very strong electric field, and those filters, when you apply a small voltage, there's a strong electric field right there to kill the bacteria and viruses. And this work, when we started, it was really nice collaboration between my group and Sarah's group in the same building. Sarah bringing a lot of expertise from the biology side.
Mm-hmm. Now, in order to use this as a water filter, there are parts of the world where you have to clean millions and millions of gallons of water. Can this be produced cheaply at a large scale?
Yes, it can be. This filter we use very low cost copper mesh and grow copper oxide nanowires right there, very easy to do. And the filtration speed is very fast. That's our intention to get millions of gallons of water every day.
Now, I understand that you work with some pretty distinguished colleagues on your team. Stephen Chu, the Nobel Prize-winning physicist, who also served as U.S. Secretary of Energy, works closely with you. What kind of contribution does he make to your work?
It's indeed very nice to collaborate with him. Last year, he came back to Stanford University after being Secretary of Energy. And he and I sat down and talk and chat about what are the most important energy problems we need to solve, and what are the potential technology can address those problems. We come down to, energy storage is one of the most important one. Both of us throw down a few ideas we all think very important. We start to work together, co-supervise graduate students and postdocs. Indeed, early this year, we have some breakthrough technology coming out addressing some of the problems has been around for 50 years.
I understand that in nanotechnology, matter at the nanoscale level has a lot of very interesting and unusual properties that you don't see at a larger scale. Can you just give an example of one or two unusual properties that people might not be familiar with when you observe matter at a really small scale?
Certainly, in the nanotechnology area, there are many examples. A simplest example I would like to give is you look at gold. It's a golden color. But once you go to the nanoscale, become nanoparticle, their color change. They can be dispersed in solution. You can see a red color showing up. That's very different from the big size scale.